Good morning, dear students. Welcome to this session on pre-stressed concrete. We are in Unit 2, solving for the pre-stressed concrete beams for the resultant stresses in the beam using the pressure line concept. The last session we have seen an example, that is what is this one. So it was the concentrical uh, pre-stressing done in the last class in the example that we have seen, right? So that is done by just finding bending moment and taking a ratio of m by b has given you the cable profile. Okay, now let us see another example where we have, for the same case of same cross section, same span, pre-stressed concrete beam of 120 mm wide and 300 mm deep, similar cross section, but of span same 6 meters to support UDL 4 kilonewton per meter is also same. The beam is pre-stressed by a straight cable carrying a force of 180 and located at an eccentricity of 50 mm. So which means if this is 300, so CG of concrete 150, right? So eccentricity of the cable means this is the location of the cable duct, right? So 50 mm from the center of the cross section. So this is 50, small e value. Okay, right. So this is 120 as usual. This is 300. Okay. But the question is to determine the location of thrust line and plot its position at quarter and central span sections. Okay, right. So just taking the given data, it is pre-stressing force given 180 kilonewton. This is a mistake even in the textbook also, just correct it. It is small e, eccentricity value 50 mm, capital A, cross-sectional area 120 into 300, 36 into 10 cube meter square, and Z value I by Y, or either you do it by BH square by 6 or BD square by 6, whichever notation you follow. So it is like 120 into 300 square by 6. Okay, right. So this value comes around 18 into 10 power 5 mm cube, right? Now, stresses due to pre-stressing force. Here we are going for the stresses calculation also, though the question is just to plot the thrust line. We'll calculate stresses also. So do it for P by A, that is direct stress from pre-stress. P is 180 into 10 cube newtons, converted to newtons, divided by cross-sectional area mm square. So it is 5 Newton per mm square is the direct pressure, and PE by Z is the bending stress from pre-stress. So P means P pre-stressing force 180, eccentricity given 50 mm, and Z is taken as calculated from BH square by 6 or I by Y, both are same. So 18 into 10 cube, it is 10 power 5. So there are mistakes that you have to correct, though it is taken from the textbook also has some typographical errors that you have to clearly identify. Okay, so it is 18 into 10 power 5 mm cube here, so that is coming around 5 Newton per mm square again. So this is direct stress. Top to bottom it is constant, which is compression, and whereas this is pre-stressing cable, which is eccentric. So you have bending stresses also. So top tension, bottom compression. So minus here, plus here, because it is going to have a hogging moment like this. So top tension, bottom compression, because you are pre-stressing the beam at no, bottom, below the CG line of the concrete. Hence, the pulling effect of bottom now will bend the beam like this in hogging position. So that is what is this. Now coming to the stresses from loads. So bending moment at center, it is like WL square by 8. So W is 4, L is 6, L square divided by 8 is written in terms of fraction. So WL square by 8 is this number. Okay, so it comes again it 18 kilonewton meter as bending moment. So going for bending stresses, M by Z. Okay, so that is 10 Newton per mm square. And resultant stresses to find at top. Okay, so we have P by A value 5, a top tension for PE by Z, and MQ plus MG, both are there in this load. 4 is uh, total live load. So a top compression, so plus 10, finally you get 10. Bottom, just reversing the signs, plus and minus will be 10 minus 10 is 0. This is the stress scenario. So finally the resultant stress at top is plus 10, bottom it is 0. So finally total compression 10 0. This is at central section. Okay, now the pressure line, this is what exactly we want. Shift of pressure line from cable line, that is lever arm. A is M by P, bending moment, and load is 180 kilonewtons. Okay, bending moment at center 18 kilonewton meter calculated, 18 into 10 power 6, nothing but WL square by 8 value, divided by P is pre-stressing force 180 kilonewton, 180 into 10 cube, finally coming around 100 mm. Whatever is calculated for the last case also, last example, the same is calculated. The only change here is the cable is eccentric now. It was concentric earlier. Okay. Now bending moment at quarter span section, we have calculated by using the formula, like if it is taking a simply supported beam having UDL. Okay. So W, something like 4 kilonewton per meter, 6 meter span. So this is like W L by 2 is the reaction. So taking 1/4 span L by 4. So we wrote a formula also. So just copy down this same as it is here, the same formula, and also the same values also, 4 and 6 for the last example. Same bending moment. Okay, it was also same bending moment, WL square by 8, 18 kilonewton meter. Same example, but of earlier it was concentric cable, now it is eccentric cable. That's the only change. Okay. So going for that 13.5, don't worry about this formula, 3 by 32 QL square. It is all after simplification you get this value. That's it. Okay. So it is like just like whatever you do, like reaction into this distance and UDL into distance and distance by 2. Okay, all that you can do it as usual, right? Now bending stress at top m by z, you do it and we get 7.5 Newton per mm square. Again finding final stresses at resultants, stresses at top and bottom. These are already there, P by A, PE by Z. This is what is at quarter span bending stress. Okay, so finally quarter span you have tensile stresses remaining, you can see, both compression uh, not of 0. So this is like 7.5 and this is 2.5, whatever is there at the bottom is 7.5 and this is 2.5. Finally, it is compression, overall compression 10 minus 7.5, so total compression. So as you move to the center, this has become 0, bottom stress has become 0, top stress has become 10. Okay. So finding a shift of pressure line from cable line, small a, that is lever arm, M by P. Bending moment at quarter span, same, 13.5 10 power 6 divided by P, 180 kilonewton, comes to 75 mm. So now you can see this point where is a 0, a value. Small a is 0 because bending moment is 0 at support. So a is equal to 0. So it starts here and 100 mm at center from cable line to the point on pressure line, it is 100. So already there is 50 mm eccentricity available. So remaining is E dash, that is 50. So E is 50, E dash is 50. Got it? So at quarter span you see the total A is 75, lever arm is 75. That means point on cable line, point on pressure line. Distance is small a, that is 75. Already small e is eccentricity is 50. So remaining value is E dash. That E dash value is 25. Okay, so 50 plus 25, total 75. So it was simple when you compare with the other example, earlier example. If E is equal to 0, means there is no eccentricity. If you move this cable to the center, this pressure line also shifts upward with the same values of 75 and 100. Earlier diagram you can see. This is like this. There's 100 here and 75 at the quarter span. Okay. Same values, so just bringing down the eccentricity. There is no change of this profile of the pressure line. So only the eccentricity value is incorporated. Hence the cable just shifted down. Okay, so pressure line has shifted down. Okay, so earlier it was 50 mm from this point, 100 mm from this point. Now it is only 50 because it has moved down by 50 mm. Same here. Earlier it was 75 above the CG line. Now it is now just 25 mm above CG line because it has moved down by 50 mm. Right. So every point on pressure line has just moved down by 50 mm. Right. So this is how, though these resultant stresses are not asked, but we have worked out for, in case if you are asked for them, it is ready reference for you. Otherwise, it is not required. Only the pressure line, drawing pressure line is required. You can see, determine the location of thrust line in the beam and plot. Okay, so only the thrust line location is to be plotted, right? So stresses to calculate is only optional for us. So we have done it as an example case. Okay, right? So that is the other example. Let us see one more example of different case. A rectangular concrete beam, 250 mm wide, 300 mm deep, Let us plot it. This is like 250. Width is 250, and depth is 300. So pre-stressed by a force of 540 kilonewton, capital P 540, eccentricity 60 mm, eccentricity 60 mm. The beam supports a concentrated load of 68 kilonewton at the center of span of 3 meters. So there is a beam of 3 meters. This is 3 meters. Now there is a point load at center. Okay, 68 kilonewtons. This is what is the given load case. Determine the location of pressure line at the center, quarter span, and support section of the beam, neglecting self weight of the beam. So take only this point load. Don't go for self weight addition. This is what is the problem suggests. Okay. Right. Work out for other the geometric quantities required. Cross sectional area 250 width and 300 mm depth. So it comes the value 75 into 10 cube square meters, right? Z value BH square by 6. B is 250, 300H square by 6. It comes to 375 into 10 power 4 cubic meter, right? Now bending moment values. Bending moment at center and quarter span, right? Center, quarter span. So moment at center is like P L by 4, right? Bending moment value. So P is 68 kilonewton, L is 3, 1 by 4 is 0.25. So that is like 51 kilonewton meter is the bending moment at center. Okay. And at quarter span, okay, it is like because of the linear bending moment diagram, if you see, it is like bending moment diagram will be like a triangle of symmetry in nature. So if you have bending moment of some x here, it will be just half of the value at half distance because it is linearly varying. So you can just straight away take half of the value, or you can work out with the reaction. So 68, so the reaction is 34 kilonewton. So we need bending moment at this point at quarter span, like 1.5 is the half, half of again 1.5 meters, 0.75 meters. So this is like 0.75 meters. So sum of all moments to the left of this section, there is only one force, 34 into 0.75. Okay, so it is like 25.5 again. So bending moment at quarter span is like just 34 into 0.75 meters. Okay, because 3 meters is the total span, half of the span is 1.5 and half of that is 0.75. Okay, so these are the bending moments. So you can also do like just to find the pressure line, you can also go for A is equal to M by P, something like this. Okay, you can plot the pressure line. Here in this example, we will try the other way of finding, like locating centroid of the resultant stress diagram. That is also by the definition of pressure line. It is like CG of the resultant stress diagram, right? So that is shown in this example. So first draw resultant stress diagram, locate CG of it. That will give you the A value directly. Okay, so let us do that. So to plot resultant stress diagram, you want P by A value. So P is 540 kilonewton, 540, 54 in 10 power 4 by cross sectional area is coming around 7.2 Newton per mm square is the pressure from pre-stress direct stress. Okay. Bending stress from pre-stress PE by Z. P E is 60 mm, Z is calculated, so it is coming around 8.6 megapascal. Now stresses from live load only, so we are not taking dead load. So already stresses are there, bending moments are there. So just calculate M by Z value. So bending moment is 51, 10 power 6. Z is 357 into 10 power. That is 13.6. Quarter span, you have just 25.5 bending moment, 10 power 6 Newton mm by Z value. So that is again 6.8 Newton per mm square. These are the stresses. So plotting the stress diagram, resultant stress diagram. Okay, so resultant stresses to calculate, it is like P by A is 7.2. Okay, say top, if you are finding a top, okay, minus 8.6, minus 8.6. At center you see 13.6. So top compression plus 13.6. So what will be the value? 7.2 plus 8, minus 8.6 plus 13.6. So that is 12.2 is the stress at top. So same way, bottom if you see 7.2 plus 8.6 minus 13.6. This is the bottom stress. So top it is 12.2, just note it, 12.2. Okay, bottom 7.2 plus 8.6 minus 13.6, 2.2. This is at center section. So this is what is the diagram. You can see 12.2 at top, 2.2 at bottom at center. Same way, at quarter span, use this value instead of 13.6. That's all. Remaining same. So you get 5.4 at top, 9 at bottom. Okay, this is quarter span. So now just locate, because this is a compression diagram, full compression. Locate CG of this one. Okay, that will give you location of pressure line. Okay. So locating CG for the center span, this is like Y1 we will calculate first. So locating CG for this diagram, so you can use the as usual methodology, whatever you have done in your engineering mechanics, by splitting this into two regular shapes, like one is a rectangle, another one is a triangle. So that will be like a1 x1 plus something like this, a2 x2, okay, divided by a1 plus a2. Okay, so this is a1. So a1 is a rectangle, 300 into 2.2 into say reference line. If it is from top, it is say, so reference line is top. So from top, this center of this rectangle is 150. Then area of this triangle, half base height, half into 300 into the remaining is just 10. This is 10. This is 2.2. So from here, from top, the CG of this triangle is 1/3 of 300. So it is 100 divided by total area. that is giving you 115 mm. So from top it is 115 mm. So that is y1 value. And if you can see the location from the CG of concrete, this is the CG of concrete, center of the cross section. So 150 minus 115 is 35. Okay, so that is plotted here. 35 mm is the essence. Okay, your way of calculating like m by p, a is equal to m by p, may be giving you like a decimal values like 34.4, something like that. So here also these values are just rounded up. You have some decimal value. So in the textbook, it is just rounded off the value. The Krishna Raju is just rounded off these values. Same way you find, by splitting this into, two shapes, two regular shapes of, one is a rectangle having 5.4 by 300 size, and 3.6 is the base, and height is 300 is a triangle. So use the same procedure to find centroid. So that is coming around 162 mm from top. So if you just locate it from the CG of the cross section, so it is 150. So remaining is 12 mm. So 12 mm below the CG line of the concrete. So this is, what is this? 12 mm below the CG of the concrete. So 0 at support, like A is 0 because M is 0. So 60 mm was the eccentricity. So same location we start drawing pressure line, and at 1/4 like 0.75 meters, 0.75 meters. So this is again 0.75 meters. Likewise, you have split all the four parts. Like so, this is locate this point at 0.75 meters, 12 mm below this line. Then locate 35 mm above this CG line. Likewise, symmetry again. Just join all those points. You get pressure line. So this is how we complete the solution. Okay, right? So this is how you can exactly practice all these examples, right? Locating pressure line and drawing it. We'll see the other cases of examples in the next session. Okay.